Your company's codebase has a bug. You ask a chatbot to fix it. It gives you text. No editor opened, no test run, no verification. You're still doing every step yourself. That's not the agent's failure, that's the fundamental limit of a system that can only produce text. GPT-4 scores 4.01 on AgentBench. A junior engineer scores 10. But give that same GPT-4 a tool to run code, a tool to search the web, a loop to try again when it fails. Suddenly, it resolves 43% of real GitHub issues autonomously. The difference isn't the model, it's the harness around it. Think of a GPS navigation app versus a human taxi driver. The GPS gives you directions. You handle traffic, reroutes, and everything else. The taxi driver, like an agent, perceives the road, decides what to do next, takes action, and loops back to observe the result. That's the agent's core loop: observe, think, act, then observe again. A chatbot runs the think step once and stops. An agent runs all three steps repeatedly, calling tools, reading results, updating its plan, until the goal is met or a budget runs out. The loop is what makes the difference. Before the agent can think, it has to see. The perception module is the agent's first contact with reality. It converts raw inputs into something the reasoning engine can process. A PDF becomes structured text. An API response becomes parsed facts. A web page becomes relevant excerpts. Without this step, the LLM receives a wall of noise. The agent's context window, its working memory, holds up to 200,000 tokens for Claude, 128,000 for GPT-4. That sounds enormous. But at step 10 of a complex task, feeding 8,000 tokens of previous observations already adds several seconds of processing overhead per call. The reasoning engine is the LLM itself. It reads everything in context and generates a chain of thought. What it knows, what it needs, what to do next. This is where the agent decides which tool to call and with what arguments. Tool schema quality matters enormously here. A vague tool description causes wrong arguments about 30% of the time. A precise, well-documented schema nearly eliminates that. The LLM then generates a tool call, a structured function invocation, and waits for the result. Each call takes 1 to 5 seconds. At 10 steps, that's already 50 seconds minimum. Here's one complete agent iteration. The agent thinks, I need to search for recent papers on RAG. It calls the search tool. 2 seconds later, the results come back. It reads them. This is the observe step and decides, not enough detail. It searches again with a more specific query. Then it has what it needs. It writes the summary. This loop, reason, act, observe, runs until the goal is met. Simple tasks take 3 to 5 iterations. SWE-bench coding agents average 90 tool calls per complex task. The capability is real, so is the cost. Here's the math no one talks about. Each step in your agent has a small error rate, maybe 15%. After 10 steps, if errors compound, you have only a 20% chance of a completely clean run. After 20 steps, 4%. An 85% accurate agent is nearly guaranteed to fail on any complex task. Then there's cost. A 10-turn research agent easily consumes 500,000 input tokens per run. Real cost. When you account for retries and full context reprocessing, runs 8 to 3, 4 times higher than the published rate. Build agents knowing the math before you hit production. Every time you see software that uses an LLM, ask 3 questions. Does it produce a single output and stop? Does it decide its own next steps? Does it call external tools? A single-shot LLM answers the first question yes, the others no. That's a chatbot. An agent answers yes to all 3, like a taxi driver who perceives, decides, and acts in a continuous loop, not a GPS that speaks once. A GPS tells you what to do. An agent does it. Pause here. This is the architecture you will build everything on.